more diagrams. Okay, and this diagram shows us how to get rid of it. Okay, I want you to focus on what is going to happen. Okay, so originally, let me get our original diagram. Okay, then you can see better at the same time. Do apologize, moving the screen a lot. Okay, so originally, as you see on the diagram above, you have a twist, right? You have a twist in the right direction over here. Okay, this is a twist direction. And I'm going to construct our shear flow. Okay, so our shear flow, the web controls the direction. Okay, so this is how the shear flow going to be, right? Okay, so this is constructing the shear flow, and for this topic F, so I'm going to call this F, and this is the F prime. So F, okay, is also the shear flow on or in the F is the shear flow acting in the flange, okay, and then V is the shear flow acting in the web. Okay, so the only way, right, to prevent the twist, okay, is to have a counter twist. Okay, is to have a counter twist direction, and F and F prime cannot generate the counter twist. Okay, because F and F prime, when they generate a moment, right, when you see them generating a moment, right, if you increase the distance or reduce the distance at the same time, both of them will not counter the twist. The only force, okay, that could counter the twist is V. So how do we counter the twist? Okay, so the only way for V to counter the twist is to have an offset known as E. Okay, is to artificially or fictitiously, okay, fictitiously. I don't think this is the right direction, or artificially. Okay, artificially. Okay, offset the V by the by a distance E. Okay, so artificially generate offset by a distance E, and this E distance, okay, this E, there's a name for it. The E, right? The E is known as the shear center. E is known as the shear center, as you can see down here. So we move V towards the left, right? So when you move V towards the left, right? So at this point, when you shift V towards the left, right, you generate a counter moment. Okay. Some of you ask me, Eugene, why we cannot move F, right? Why do we not move F? Okay, because we don't, even F is at this position, right? We already have a twist in this direction already, right? We cannot change the direction at all because it's controlled by the web, right? The shear flow is controlled by the web. So you cannot just move one up and fix F at the bottom. You cannot do that. If you move the F up, you have to move the F away in the same distance. So the best way to do is to move V. Okay, so you do an offset. Okay, so this is showing what is actually happening, right? You move an offset by E. Okay, so you have a counter twist. So by having the E over here, you are generating a counter twist. Okay, this counter twist will eliminate the eliminate the twist. Okay, so E is a distance. Yes, E is a distance. Okay, right. So now we are going to take moment about point C now. Okay, so I'm going to get this diagram again. Okay, so I'm going to call this point C. Okay, exactly at the center down here. I'm going to call this point C. Okay, so we're going to take, so we're going to focus, so we know that over here we have our applied force F, or shear flow F over here. All right, and then this is that is the centroid, and we're going to call a distance to F. Okay, so distance, this is H over 2. Okay, so we are going to do, so if this is our transformation, okay, so this is our Y, this is our Z, this is rotation in the X. Okay, so we are going to take summation about moment on the X direction at point C, right? And the whole thing will be equal to 0. Okay, the whole thing will be equal to 0. Okay, so we're going to take the moment now. Okay, so we will have, so at point C, the F, right, will have a clockwise, sorry, anti-clockwise direction. So F multiplied by H over 2. The bottom F is also plus by F multiplied by H over 2. And then we are going to calculate plus B multiplied by E. The whole thing will be equal to 0. Okay, so V E is equal to FH, or minus FH. So E is equal to minus FH over V. Okay. So what you realize is, note that E is going towards the left, right, relative to point C. Okay, so therefore, right, towards the left, therefore, usually right is positive, left is negative, right? So therefore, it is negative. Okay, so usually what we tend to write, we just take it like E is equal to FH over V. Okay, if you look at textbook, it's always in the expression, and we know when it's negative, it's on the left hand side of point C. Okay, right. So the next thing that we are going to do, so how do we relate, okay, or how do we determine E, okay, which is the most critical part. So the first thing we're going to do is how to find F, okay, how to find F. So to determine F, right, to determine the force, right, so let's say if it's between A to B, right, so we're going to integrate from point A to point B, right? A and B is basically between these 2 points, right? It can be equal to, we integrate between the limits A to B, Q, shear flow, multiplied by ds, where Q is equal to VQ over I, right? And the units over here, we know that it is equal to Newton per meter. Okay. Now it can, so you can use Q, or you can also use F, okay, between A and B. You can also use the shear stress, right? And you multiply T multiply by ds. Okay. ds is the linear distance. Later on, I'll show you what we mean by that. And this is equal to the shear stress is equal to VQ over IT. And the units over here is in Newton per meter squared. Okay. So the T over here is the thickness, is the thickness geometry perpendicular to the shear force. Okay. Okay. Now that is enough theory. Now, okay, I would like to do one example, or I'd like to do 2 examples. Okay, to deal with this topic. And as I said, this is like one of the easier topic in shearing stress. Okay, so let's look at one example or 2 examples. Okay, so this question asks us to determine, right? Determine the location of the shear center O of a thin wall section of uniform thickness having the cross section shown. Okay, right. So first of all, we are going to before we go on, I want you to observe this diagram. I'm going to pull out. Yeah, I'm going to expand it. I want you to see something. Okay. So what is I want you all to pay attention on how the dimensioning is done. Okay, what do I mean by